Hey everyone, welcome back. Today we are diving into one of the most fascinating topics in your class 12th AI syllabus, making machines see, also known as computer vision. This is unit 3 and trust me, ये topic बहुत important है for your board exam. So get your notebooks ready because in the next few minutes we are going to completely demystify how machines can see, understand, and even make decisions based on images, just like you and I do every single day. Let's get started. Let me start with a question. Have you ever uploaded a photo on Instagram? Of course you have. Now, billions of photos are uploaded every single day across Facebook, Instagram, Twitter. And here's the interesting problem. When you type red apple in Google, it finds text results easily. But if you show Google an image and ask, hey, what is in this photo? That is a completely different and much harder challenge for a computer. You see, traditionally, images were described manually using meta tags and captions. That's slow, impractical, and simply doesn't scale. Now think about how a child learns. You show a 2-year-old an apple again and again, apple, apple, and after some repetitions, they recognize it instantly. Computers need to learn the same way. We show them thousands of labeled images and train them on patterns, and they start recognizing objects on their own. But here's the key difference. Computers don't see images the way we do. They see numbers. Bridging this gap, that is exactly what computer vision does. समझ आया? Let's move on. Alright, so now let's nail down the official definition because this is a guaranteed exam question. Computer vision is a field of artificial intelligence that uses sensing devices and deep learning models to help systems understand and interpret the visual world. Write this down. And here's a bonus point. Computer vision is also called machine vision. This has come up as an MCQ multiple times. CV is also known as, and the answer is machine vision. Don't forget this. Now here's a beautiful analogy. In human vision, your retina captures light, the optic nerve transmits signals, and your visual cortex processes meaning. In computer vision, the camera is your retina, the data pipeline is your optic nerve, and algorithm is your visual cortex. It's literally replicating human vision, but in a machine. And the most exciting part, the latest deep learning models have actually achieved above human level accuracy in tasks like facial recognition and object detection. Machines are literally seeing better than us in some tasks. Mind blowing, isn't it? Okay, now the most fundamental question. How does a machine actually see? Imagine zooming into a photograph, like really close. You will start to see tiny little captured squares. Those are called pixels, short for picture element. A digital image is nothing but a huge grid of these tiny squares, and each square stores a number. For a black and white image, pixel value 0 means pure black, pixel value 255 means pure white. Everything in between is a shade of grey. For a color image, we use the RGB model, red, green, blue. Each channel stores a value from 0 to 255. Now here's the maths. 1 byte equals 8 bits. So 2 to the power 8 equals 256 values. Multiply 3 channels together, 256 into 256 into 256, and you get over 16 million possible colors. That's why your phone screen can show such rich, vivid images. Look at the pixel grid on the right side. That's literally how computer sees an image. A matrix of numbers, no colors, no beauty, just digits. And from these digits, the machine has to learn everything. More pixels equals higher resolution equals more detail. ये remember करना है. And binary art is a great hands-on the way to actually see this yourself. Now here's a slide that will get you marks in the exam. The 5 stages of the computer vision. This is a structured pipeline. Every stage feeds into the next. Stage 1, image acquisition. Captures the raw image. Think of camera, scanner, MRI, CT scan. Stage 2, pre-processing. Clean and prepare the image, remove noise, resize and normalize. Stage 3, feature extraction. Pull out meaningful patterns, edges, corners, textures, colors. Stage 4, detection and segmentation. Find and classify objects within the image. High-level processing is stage 5. Use all that information to understand the scene and make intelligent decisions. Think of it like this. It's an assembly line in a factory. Raw material comes in at stage 1, gets refined at each step, and a finished intelligent output comes at stage 5. Now, important exam tip. These stages always come in this exact order. Image acquisition is always first. High level processing is always last. Let's zoom into the first 2 stages now. Stage 1, image acquisition, is where everything begins. The principle here is simple. Garbage in, garbage out. If the quality of your input image is poor, your entire CV system will fail, no matter how good your algorithm is. Images can be acquired from digital cameras, scanners, design software like Photoshop or Paint, and in the medical field, highly specialized devices like MRI, CT scans. These help doctors see inside the human body at the incredible detail. And computer vision helps analyze these images automatically. Lighting conditions, angle of capture, device resolution, all of these directly affect image quality. Moving to stage 2, pre-processing. Think of this as the editing room of the computer vision. We have 4 main techniques. 1. Noise reduction. Removes grainy effects, blurriness, random distortions from the image. Second, image normalization. Scales all pixel values to consistent range like 0 to 1, so the model learns better. Stage 3, resizing and cropping, making all images of the same size. A very common standard is 224 into 224 pixels, used widely in neural networks. 4. Histogram equalization. Adjust brightness and contrast to make dark or dull images sharper and more detailed. The goal of pre-processing is simple. Remove noise, highlight important features, and ensure uniformity across the data set. Now we get to one of the favorite stages, feature extraction. This is where the magic really starts. Think about it. When you look at a photograph, your brain immediately notices the outline of a face, the texture of a fabric, the color of a fruit. You don't consciously think about it. It happens automatically. Feature extraction is computer's version of exactly that process. We have four key techniques. Edge detection identifies the boundaries between different regions where there's a significant change in pixel intensity. Imagine tracing the outline of face in a photo. That's edge detection. Corner detection finds points where two or more edges meet. These are areas of high curvature. Think about the sharp corners of a building. Texture analysis extracts features like smoothness, roughness, or repeating patterns. The difference between rough stone and smooth silk. Texture analysis captures that. Color-based feature extraction quantifies color distributions to distinguish between objects. Classic example, detecting ripe versus unripe tomatoes, or you can say detecting red versus green tomatoes in food processing factory. And here's the most important line for your exam in deep learning approaches. Feature extraction is performed automatically by CNNs, convolutional neural networks, during the training process. You don't need to manually define features. The network learns them on its own. That's the real power of deep learning. Alright, this is stage 4 and it has a few subparts, so stay focused. Detection and segmentation is about finding and identifying objects within an image. It's critical in applications like autonomous driving, medical imaging, and security systems. We split this into two categories: single object tasks and multiple object tasks. Single object tasks classification simply tells you what the object is. Is this a cat or a dog? Just the class label. The algorithm used can be KNN for supervised classification or K-means for unsupervised classification. Classification plus localization gives you the class and draws a bounding box around it. This is a cat and it is located right here in the image. Multiple object tasks. Object detection identifies and locates multiple objects simultaneously, draws bounding boxes around each one, and assigns class labels. The key difference from classification. Classification treats the whole image as one thing. Detection finds every individual object. Famous algorithms are CNN, RFCN, YOLO, you only look once, and SSD. YOLO is favorite MCQ, remember it. Image segmentation goes even deeper. It creates a pixel-wise mask for each object. Two types: semantic segmentation groups pixels by class, all animals together regardless of which animal. Instance segmentation separates each individual object. Dog 1 gets one mask, dog 2 gets different mask, even though both are dogs. Now, quick memory trick. What is equal to classification? Where is equal to localization? What plus where for many objects is equal to detection, and every pixel is equal to segmentation. And Here we are at the final and most intelligent stage, high-level processing. By this point, the system has acquired the image, cleaned it, extracted features, detected and segmented objects. Now it needs to actually understand what all of this means and take action. Let me give you the best example. A self-driving car. The cameras have captured the road, pre-processing is done, features extracted, objects detected, pedestrian crossing, red traffic light, another vehicle. Now high-level processing kicks in and says red light ahead, slow down and stop. Pedestrian in the crossing zone, so do not proceed. Tasks involved include object recognition, scene understanding, contextual analysis, and ultimately intelligent decision making. In healthcare, a CT scan is analyzed and the system identifies early signs of tumor. That level of insight comes from the high-level processing. High-level processing empowers computer vision systems to extract valuable insights and drive intelligent decision making in various applications. That line is perfect for long answer conclusion. Now the fun part. Real world applications. These are all directly from your handbook. You have probably interacted with most of these today itself. Facial recognition. Facebook, Facebook automatically tags your friends in photos. Phone unlock with your face. All of what is computer vision at work. Healthcare. CV evaluates cancerous tumors, identifies diseases and abnormalities from medical scans. Doctors use it as a powerful diagnostic tool. Self-driving vehicles. Cameras on all sides of the car capture the environment. CV detects other cars, reads traffic signals, identifies pedestrian paths. Tesla does this every second. OCR, optical character recognition. Take a photo of printed invoice or a handwritten document and CV extracts the text automatically. Banks use this constantly. Machine inspection. On a manufacturing line, CV checks thousands of products per minute for defects, features, and functional flaws, far faster and more accurately than any human. 3D model building. Constructing 3D computer models from real objects used in robotics, autonomous driving, AR and VR. Surveillance. CCTV systems with CV can identify suspicious behavior, detect dangerous objects, and help law enforcement maintain security. Fingerprint recognition and biometrics. Your Aadhaar verification, your phone's fingerprint scanner, all powered by computer vision. 8 applications, all from the handbook. Try to write them out from the memory tonight. Now, as a powerful computer vision is, it's not perfect. There are significant challenges. Let's go through all 4. Challenge 1. Reasoning and analytical issues. Computer vision needs more than just image identification. It needs accurate interpretation. For example, seeing a knife in an image, is that a kitchen knife or a weapon? The context matters enormously. Without robust reasoning capabilities, extracting genuinely meaningful insights becomes very difficult. Challenge 2. Difficulty in image acquisition. Lighting variations, different angles, complex scenes with multiple objects, occlusions where one object behinds the another, all of these make it really hard to consistently acquire high quality images for accurate analysis. Challenge C. Privacy and security concerns. This is a big one in today's world. Facial recognition and serverless systems can track individuals without their knowledge or consent. Technologies like deepfake raises serious ethical questions. Governments are actively debating regulations around these technologies. Challenge 4. Duplicate and false content. Malicious actors can exploit CV algorithms to create fake, misleading content. Deepfakes, doctored videos, data breaches lead to spread of duplicate images, causing misinformation and serious reputational damage. For your exam, a quick way to remember all four: RIPD: reasoning, image acquisition, privacy, and duplicate content. Isn't it easy? Now, let's look at where computer vision is headed, and this makes for a great conclusion in any long answer. Over the years, CV has evolved from basic image processing tasks, simple edge detection, and shape matching, to incredible complex systems that can understand and interpret visual data with human-like precision. The breakthroughs in deep learning, combined with vast amounts of labeled training data, have completely transformed the field. Look at the future. We are talking about personalized healthcare diagnostics, where AI analyzes your scans better than any doctor. Immersive AR and VR experiences, fully autonomous vehicles navigating complex environments. The possibilities are genuinely awe-inspiring, but with great power comes great responsibility. By embracing innovation, fostering collaboration, and prioritizing ethical considerations, we can truly harness computer vision for the benefit of humanity. Alright everyone, rapid fire recap. I'll say the question, you recall the answer. What is CV? AI field using sensing devices plus deep learning, also called machine vision. How does a computer see? Pixels, monochrome 0 to 255, color RGB 16 million plus colors. How many stages in CV? 5. Acquisition, preprocessing, feature extraction, detection segmentation, high level processing. 4 pre-processing techniques: noise reduction, normalization, resizing, histogram equalization. Feature extraction types: edge, corner, texture, color. CNNs automate all of this in deep learning. 4 challenges: reasoning, image acquisition, privacy, duplicate content. If you get all of these right, you are absolutely ready for unit. And finally, practice time. These slides have CBSE pattern questions, MCQs, short answers and long answers, all with complete model answers. For MCQs, answers are machine vision, image acquisition, black, class and object detection. Write these down and revise. I want you to close this video and write out at least one long answer from memory. That's the best exam preparation you can do. All the best, everyone. You have got this. Do like the video, share it with your classmates and subscribe for more class 12th AI content.